All right, thank you, Berko. So yeah, look at the picture. Robots serving burgers. Isn't that awesome? That's what we're going to talk about today. So the title, Real-Time Speech Recognition, Best Practice for Scale and Performance. So we're going to dive deep into how this robot does its job, basically. So a little bit about me. So my name is Emil Loer. I am the lead architect of HiAuto, and we are the market leader in conversational AI for restaurant drive-thrus. What that means is basically, there are things which are called quick service restaurants, which are basically restaurants where you order food and you take it out, for example. Sometimes you can sit in, but they're basically like your McDonald's, your Burger King, that kind of stuff. And a lot of these places, especially in the United States, they have drive-thrus where you drive with your car up to a speaker post, you talk to them, you order, and then you get your food all from within the car. You don't have to leave. Super convenient, and you can get on with your commute or whatever you're doing. So I will be using this as an example, and I'll be telling you a little bit about how we approach like the scaling setup for our speech recognition, a bit about how the technology works. But the things that I'll be talking about are kind of, there are things in here that you can use for your own projects as well. Of course, depending on what you do, but in general, everyone at some point, if you do your work right, has to come across some kind of scaling problem. So we'll see where that leads us. So let's talk about the drive-thru. So basically, it starts off with a restaurant guest, right? Someone decides, like, okay, I want to go to a drive-thru because I'm hungry. I want a burger. We know the feeling, right? So you get the munchies, and so you say, like, hey, can I have a burger? But of course, if you just speak and nobody's listening, nothing's going to happen, right? So we have to introduce another actor into the game, and that's a restaurant employee. So the restaurant employee will listen to what the guest has to say. And so the guest says, I want a burger. The employee might say something like, okay, that's fine. But typically what we want employees to do in a restaurant like that is attempt things like upselling, for example. So they have a script that they follow. They might say things like, okay, you want a burger, that's good. But on the menu we have a combo, so would you like some fries with that? And the conversation continues, and the guest might say like, oh, sure, that sounds good, and you know what, I'll also add a cola to my order, and that's it. And then the employee will say, okay, that's $7.99 or however much it is, thank you, drive-thru. And this concludes an entire interaction with a drive-thru. As you can see here, there's a bit of repetition here because you can see there's things going back and forth between the guest and the employee. So we can disassemble this a little bit, and we can convert this into building blocks. And these building blocks are called turns. And what is a turn? It's basically this part where the user says something and the employee returns an answer. And this, this back and forth thing will result into an entire interaction or conversation or whatever you want to call it. So what HiAuto does is we automate this. We basically say, okay, we take the restaurant employee out of the equation, at least for this part of the order taking process, and we replace it with an AI that you then talk to. Now, of course, the employees are still in play because they work behind the scenes, they take the payments, they actually cook the food and stuff. We don't have robots for that yet, and it's a question of whether we should or not, but anyway, we are focused on the order taking. So, okay, so let's make this into an AI. So there's a very simple step that we have to do. We just have to replace this employee, right? Okay, so here we go. Now it's a system. Our project is done. Let's ship it. Let's earn a lot of money. End of talk. Goodbye. Unfortunately not, because we have to figure out how to do this, right? This is not easy. You can't just say like, okay, we'll place a computer in the restaurant and we'll put it next to the window and it'll do its thing. There is some trickery involved. So let's see what actually goes on behind the scenes. So let's get some room here. And basically, in a conversational AI, there's several components that are at play. Now, there's more than I will mention here because it's a very complicated subject, but I'll break down the three most important ones. And then, there's a lot of stuff happening on the side, but not too relevant for the contents of this talk. Anyway, let's start. So the guest says what they want, right? I want a burger. So the first thing that we have to do is we have to figure out what the user is saying. So what we have is a component called automated speech recognition. This is the main focus of what I'm going to be speaking about today. Automated speech recognition basically means take what the user is saying, make a transcription of it. So then we know what the user is saying. but we don't know yet what they actually mean. Like, for example, we know the words, but we don't know, for example, like do they want a burger? Do they want a large fries, a small fries? Do they want a milkshake with whatever flavor they want? Does it have to be combined to do a combo or whatever? So we need to perform some natural language understanding. So basically what we do here is we take the transcription from the speech recognizer, and then we try to do like named entity recognition, and we try to find like relationships between these entities. We figure out their intent and a whole bunch of other stuff to figure out what they're actually talking about. And then, now that we know that, we can make business decisions based on that. We can, for example, say like, okay, you know, they ordered a burger. Now it's time to ask for an upsell for fries or whatever else. So that's basically the three pillars of a conversational AI. As I said, there's much more because you have to interact with other systems as well, but it's not really, really relevant for now. Instead, what I want to do is I want to focus on the automated speech recognition. Basically, what we're trying to do is we're trying to have a realistic conversation with, between an AI and a human. And the realism is important here because time is money, but at the same time, you know, when things take too long, people get frustrated, quality goes down, and all of that stuff. So basically, the faster you respond, the better. So automated speech recognition. What is it and how does it work? So first of all, we start with speech, right? What is speech? Well, in this case, speech is recorded audio. So what that means is we have an audio device somewhere that captures the audio. The audio device can be your phone, it can be some kind of audio interface, like you know, one of those musicians' interfaces, for example, or it can be, you know, something that you already have, like a pre-recorded sound clip that comes from somewhere. Doesn't matter. Anyway, so we have recorded audio, but it's not yet suitable for speech recognition because we have to apply some kind of steps to make it compatible with that. We have to apply resampling and pre-processing. And what I mean with that is the recorded audio might not be in a format that is easy to work with from an AI perspective. At the same time, there might be noise in here that we might want to remove, anything that makes it easier for a speech recognizer to work. And so a part of this is also like resampling, which you can essentially see as dimensionality reduction, and that's of course important in making your models work better. So then we have a signal that is in the time domain. However, speech recognizers are not very good at working at the time domain, and I'll tell you why. Typically, audio is like a waveform, right? And so what you could do, for example, is you can look at like the shape of the wave and stuff like that, and that'll give you things like the period and everything. But human speech is not like a single waveform all the time. It's much more complex than that. If we were to build, for example, a guitar pitch recognizer or something like this, this would be fine. You just put an autocorrelator on it and it would work. But with speech, you have to look at things like phonemes, formants, and all that kind of stuff to distinguish the different, for example, vowels and consonants. And our speech, you know, as I talk to you, you just listen to it. If I say things like the letter S or something, or the letter V or whatever, then you see that there's also some noise in the signal. This is good noise. It's not noise we want to filter out, but it's noise that we can use to recognize certain sounds in the words that we're saying. And so what we have to do is we actually have to look at the frequency domain. So what we do is we apply an FFT step. And then what we can do is we can look at the spectrum, and inside the spectrum we can find patterns. For example, we can find the distance between certain frequencies that we say in a word, and that will give us formants. For example, the difference between an A and an O. Very important to know, of course. Now I say FFT here. Sometimes the FFT is applied twice to work on the cepstral domain, which is like the FFT of FFTs. Different techniques are used here. Bottom line is you have to at least go to the frequency domain. Okay, so you've got that signal, and now what you have to do is, of course, use your magic models and get some kind of prediction out of that. Now, there are many types of models that can be used for speech recognition. You've got like the traditional like hidden Markov model and Viterbi type stuff. There's also recurrent neural networks. There are experiments with deep learning. There's all kinds of stuff that's being done right now. I won't go into depth into how these models work. If you're interested, talk to me afterwards. I'll be happy to explain more. Anyway, so model does its thing, and it returns some kind of output. So what does it output? Well, a transcription. what is a transcription? So a transcription typically is the words that we're saying, right? So that's the stuff that we're interested in. But we're not always just interested in the words. Sometimes we're also interested in the timing between words, because if we notice that the user starts speaking slowly somewhere, we might be able to detect hesitation. We might also be able to use that for separating sentences and that kind of stuff. It's all useful input. So you want to augment this with metadata during the prediction, and then do something useful with that. So this is automated speech recognition in a nutshell. So I'm going to highlight a few things here to tell you a little bit more about some design decisions that are made when building such a thing, and then later on we're going to talk about how to scale this up and how to actually keep getting good performance out of it. And here, when I say performance, it's important to know that I'm not talking about the accuracy of your model, but I'm talking about the actual performance of inference, as in how much speech can we process, how much speech can we detect in a system at scale concurrently. And of course, this is good because it means we have to use fewer resources and we can save a lot of money. So let's start at the top. So we have to get a good audio signal to start doing our speech recognition. Very important, because if your signal is bad, if it's poor quality or whatever, then no matter what you do with training or with inference, it will just not be very good. I mean, it won't be able to recognize all of the speech that you're saying. And especially if your main source of audio is already noisy to begin with, as in our use case where people are talking from within a car. You know, the car makes noise. Some people even on motorcycles, they make a lot more noise. Or trucks, it might be more distance between the speaker and stuff. It gets complicated. So you want to get as good of a signal as you can to begin with. So good hardware is important here. Now, what you could do is you could get like professional audio recording interfaces. They'll give you very pristine recordings. They have like good analog to digital converters in there and all kinds of stuff like that, high quality electronics, and that will help. Now, of course, not everyone is working with that. Some people might say like, you know, I want to build speech recognition that works on phones. Well, phones have like tiny microphones, and so you have more problems there. You might want to spend some time cleaning the signal up before you send it out. But anyway, good quality hardware will definitely help here. Good microphones as well, of course. So, so then we have our signal there, but we need to then capture it into some kind of format. And there's this quote. You may have heard of it. It's, I believe, from some guy at Microsoft or something. He said at some point like 16 kilohertz ought to be good enough for everybody. So basically, what I mean with that is, audio is captured at a sampling rate, right? So we take samples every n times a second, basically, and that forms our from that we can reconstruct a waveform. Now, typically, what we do with modern audio, like especially like if you have like Blu-ray stuff at home or whatever, it's 96 kilohertz, so it's incredibly high, which means there's a lot of fidelity in the sound. However, there's a gotcha here, and that is that the human ear is not able, you know, for a healthy young individual, is not able to hear any sounds that have pitches higher than 20 kilohertz. So basically, any information above that is not useful for recognizing speech, because if it were useful, then our ears would have been equipped with you know, features to detect anything in there. But it's not the case. So we can safely discard any of that. Now you might say like, okay, you know, but why then are these DVD players or whatever, why do they use such high audio quality? And the reason is that this gives more headroom for maintaining good quality when you do a lot of audio processing steps on it. Because every time you do a processing step, you introduce noise in the system. If you have a high quality signal to begin with, you reduce the chance that that noise will propagate through. But for our case, it's not really that important, because all we are doing is basically downsampling it, and then we're doing inference on it. We might do some filtering and stuff. We can do that while it's at the high input frequency, but the speech recognition itself doesn't have to be more than 16 kilohertz in this case. So I said 20 kilohertz is the max range that most people can hear things. Now, of course, because of like Nyquist sampling theorem and all that kind of stuff, that means that to hear a 20 kilohertz signal, you need double the sampling rate. So 16 kilohertz is not 40 kilohertz sampling rate here. So what's going on here? So the basic idea is that there's been a lot of research, and we've discovered that you can actually do speech recognition perfectly fine with just frequency content of up to 8 kilohertz. Everything else is just redundant information, basically. So this is a really good compromise between getting good performance and at the same time reducing your the amount of data that you use. The last thing I want to talk about here is color. So every operation that you do, especially on the hardware side, adds color to a sound signal, which means that there are slight nonlinearities introduced and other things. And the entire idea behind that is that you have to make sure that if you do training on recordings from one audio source, that your prediction is going to be on something that is similar, or at least contained in the training data set. Because if audio devices are different, you're going to get different performance as well. So that's something to consider. So let's talk about architectures. Because we now know how speech recognizer works, but let's build one, you know. What kind of design decisions do we have to make here? That's the question. The first thing that comes to mind is offline versus online, or online versus offline, as I wrote it here. Basically, the idea is, like for example, in a restaurant drive-thru, what you could do is you could place a computer over there and you can have it do speech recognition. And it's very close to the user, and it's great. At the same time, what you could also do is you could say, like, you know, I want to keep everything centralized, and I want to do the speech recognition somewhere, you know, in a cloud or whatever. And these have different trade-offs. As I said, doing things where you respond quickly is important, right? So you would think like, okay, if I do this closer and I do this online, this is very good because I get very fast response times. At the same time, you know, you could also do offline. You could say like, okay, I'll record everything until a point with which I know that there's no speech happening. I send it off to the cloud and I do something very expensive on it, very massively parallel or whatever, and I get answers that way. It's another possibility. You get different results in either case. Typically, we favor in real-time speech recognition online. That's also where the term real-time comes from, of course, because we can respond instantaneously to things that the user is saying. For example, a lot of speech recognizers do live transcription, right? If you're talking and you keep talking and you don't stop, it won't wait until you're done speaking, but it will actually transcribe as you go. And you can actually use this information because you can say, you can make decisions while the user hasn't even finished speaking yet. In some languages, for example, at the beginning of the sentence, it's easy to detect the intent already. So you can use that information and then, you know, expedite certain decisions that you have to make. There's also precision versus speed, and this has to do with, of course, like, you know, how do you want to train your models? Do you want to use like floats and everything that are like high precision, or do you want to lose a little bit of accuracy but gain a lot of computing power? This is not so much a thing as to like how you get good ASR, because of course precision always wins there, but when you scale up, you have to think about using your resources effectively. And the entire idea is that if you can squeeze more out of a server, especially costly servers, then you can save a lot of money. And so it's a good idea to think very carefully about, okay, where is this point at which, basically what can I get away with? What kind of optimizations and stuff like that? And I briefly mentioned already, edge versus cloud is also very important. Placing things at the edge typically is faster, but then you have to put your model somewhere, in our case in a restaurant or somewhere, and it just, it becomes more of a burden to maintain that. Whereas in the cloud, everything is centralized, so basically everything fits in a cluster. You can have all this nice ML ops and stuff to automate that. Fantastic. But at the same time, you have to get the audio data to your cloud, and that involves audio streaming. And audio streaming is a place where a lot of things can go wrong. So once again, a trade-off that you have to think about. The bottom line is you have to optimize for latency. Anything, I've said it before, but this is a very important theme, and it's a thing with everything else, because for example, last night I was making these pictures that you saw at the beginning of the slide, and boy, was that Dolly server slow. It's not fun to interact with such a thing, right? And so this applies everywhere. Whatever service you have, make it fast enough so that people don't get frustrated. Plus, an AI that takes too long fails a real-time Turing test, you know? If you, as a customer, drive to the drive-thru, you say, I want a burger, and you hear nothing for 30 seconds, and then you hear some crappy voice giving an answer, it's not good, right? It's you think like, who am I talking to? And you start to get irritated. You give irritating reactions, and we hear this in recordings from how people interact with our system. They don't like it, but if it responds quickly, they don't have a problem with it. It's fun. It's like it's a modern technology you're interacting with, and it's it doesn't cause too much trouble. So those are things to look for when you're designing such a thing. Now, okay, so you've built your speech recognizer, and you start talking to investors, and your investors are saying like, oh, I like this, what you're doing. I'm going to give you a bunch of money if you can get 10 customers. So we got to scale up. Oh boy. So first thing to do is look at like, okay, what kind of data are we moving around? And so in our case, what we are doing, we have an online solution, and we use a centralized environment for reasons I will talk about later. But that means we have audio streaming going on. And so with audio streaming, there is network communication, and so there's bandwidth that we're using. Now, if we want to get good scale, we might have to think about how to reduce bandwidth here. And you could just say like, okay, I'll compress everything, because that's typically also what's been done in HTTP and stuff. You can just use deflate or gzip or whatever, and send things. And with audio, it's pretty straightforward that you can do that, because I'm pretty sure that all of you have pirated MP3s in the past, and so and the reason why you used MP3 was because it's small. You didn't have to wait so long for a song to download, right? It's great. So we can use that here for speech as well. However, we're not going to use MP3, because MP3 is a music format, and there's better things out there, especially for speech. It turns out there is a codec called Opus, and Opus is basically a codec for speech and for music, and it's used in a lot of places, like WebRTC uses it. It's used behind the scenes in YouTube, so if you watch YouTube videos, you actually get it in this codec. And it's built into browsers, which is also very useful, and a lot of other great things. And this gives you super small packets that you have to send, and so you can send more data. But what better way to optimize bandwidth than not send data at all, right? Sometimes you know that the user isn't speaking. So what you can use is a technique called voice activity detection, where you place a tiny model or even an algorithm. You can even look at like the amplitude of a signal and make some conclusions based on that. You place that at the beginning of your signal chain. And then what you do is, based on that information that you get, you decide whether or not to actually feed things into the Opus decoder, saving CPU, and then feed it through the network, saving bandwidth. So effectively what you're doing is you're pausing the audio stream, which is really good, because that means that basically all of the parts of the system that are centralized, that are more expensive, like your GPU machines or whatever, they don't have to do any work. They can spend their time on something else. You save a lot of money that way. Plus, you can use this pausing information for something else too. If you know that the user isn't speaking, you also know that it's safe for you to reply, because you don't want to cut off someone, right? That's very rude. So, okay, so we've optimized our bandwidth and all of that stuff, and we got our 10 customers, and that's great. So we start talking to our investor again, and the investor says, oh, I'm impressed with your MVP. This is really good. I'm going to give you more money, but I want you to have 1,000 customers now. Oh boy, here we go again. So now we're going into the domain of really hardcore optimization, and what this means basically is we can't just look at like our speech recognition technologies as to like how models are working and all that kind of stuff, but you actually have to look at the inference side and how we can do things fast, how we can orchestrate our components in such a way that they work fast and all of that. And there's once again certain trade-offs and decisions that we can make. So let's highlight a few of them. The first thing that we all should do, of course, is we should speak the right language. Now, what I mean with that is I don't mean like, when you build a speech recognizer for English, don't speak Dutch into it because it won't make sense of it. No, I mean, that's pretty obvious, right? No, that's not the point. I'm, of course, talking about programming languages here. And so typically in the ML community, a lot of people use Python. And Python's great for prototyping and stuff. But once you go to production, you discover that a whole lot of aspects, especially related to very high scale, Python is actually really bad at. The problem is you have things like GIL, you have things that there's no good optimizer behind it and all that kind of stuff. We're talking about super high scale here, right? It's not like just spinning up multiple processes, but we want to squeeze every little drop out of our machine that we have. You have to think about the programming languages that you use and which one is the best for your job, for the job that you're trying to do. Like for example, part of our solution is audio streaming, right? Python is not a good streaming language. You might typically want to go and move that component to, say, a language like Go, which has superior network capability, or Rust, which can do similar things and use less network. Or you might be a masochist and go C++, whatever. I don't care. There's a lot of things you can do there. But basically, all of these languages have their strengths. I'm not saying write your entire project in Rust, even though I would love that. But the thing is, it also slows you down, right? You have to think about how you can keep iterating on your features as fast as possible. And typically, application logic does not have to be in such a small, such a fast, optimized type language. It would just create more of a burden than it actually adds value. Plus, you have to think about the team that you have, right? If you transition to a tricky language like that, you have to make sure that everyone understands it as well, and that might, of course, be not the resources that you have. So there's also process separation. Use different processes for different things so you can put them in different machines, like put your AI in one place, put your business logic in some other place. Don't have them share the same machines, would be very slow. And also use dedicated node types. Like for example, if you use Kubernetes, then you might want to have one instance type that is dedicated to high network, one that's dedicated to high CPU, and so on. You can get a lot of value out of this, but even more importantly, you can save a lot of money as you scale, which is also important, right? You don't want to waste resources because it's just going to cost you. And especially at scale, machines are expensive. Another thing to consider is some machines have like very high capacity, others might have low capacity, but you can spin up more of them cheaper. Those might actually be better. Don't think that a fast machine is always better. It might be that multiple small ones will actually do the job better because you can parallelize. Something to consider. And finally, what I would like to talk about is a little bit about the CPU versus GPU debate. A lot of models these days use GPUs. Also for inference, because GPUs are very fast, they're very good at massively parallel operations, tensor computations, that kind of stuff. But there's a cost, and it's often overlooked, and especially when you do a lot of short inferences, GPU has a startup cost. And if you cannot keep a constant stream going, but you have to start and stop things, or you're using your GPU for other things, which I would not recommend doing, but sometimes you have to, then GPU can be slower, and it might actually pay off to do some of your inference work on CPU. So think about this carefully. Take metrics. It will give you all the answers that you need, especially like latency metrics. So with that, I've given you a lot of things to think about. A lot of this stuff is not necessarily related to speech recognition, but you can also apply this when you do video recognition or even like massive text inference or whatever. It's, there's a lot of things to think about, especially as you go at high scale. So to close this off, I would end up with a quote. Your model is only as good as the speed at which it predicts. So make sure that it's fast, especially when you get to production, and yeah, that way you can move the world. So thank you.
Thank you very much. There's time for one question, I think. Jan Salvador, there you go.
Thanks. Other way around? Yeah. No. It's like that, right? Yeah. Thank you for the talk. I was thinking, so in your case, the output of your system is quite limited because you know the menu, right?
That is correct.
Yeah.
And you can use that to your advantage.
Yeah, I was wondering, so how did it affect back to the speech recognition part? So did you, were you able to have some shortcuts there because you know that the output is very limited?
Absolutely. So let's take an example here. So we all have a speech recognition in our pocket, right? It's called Siri. So if you talk to Siri, it's very often unclear what, it is not certain what you mean, right? Because it has been trained on a huge domain. If you have a very specific domain, say like a restaurant menu, and you use that as your language model that you use for your speech recognizer, then of course you can bias the weights of each of these words inside there to be more relevant for your data set. And so when someone says like burger, it's more likely that that is actually transcribed as a burger and not as some other word that sounds similar, right?
Yeah.
So thank you very much, Emil. We'll give him a big hand. Thank you very much. I have a question for you.